Let's Make It is brought to you by Ting, the new way everyone is getting their cell service. No overage penalties, great rates, keep what you do not use, no contracts, and someone will actually pick up the phone when you need support. Use our link and get $25 off your first month's service or your new phone. Just go to tech-zen.tv/ting to save $25. Hello and welcome to another episode of Let's Make It, the show where we show you how to make things with Arduinos and all kinds of fun electronics. This is episode 36 and is recorded on September 16th, 2013. And I have with me, as always, Bob Powell. So say hi, Bob.
Hey, Mike. How are you?
All right. How you doing?
I'm doing good tonight.
Looking good?
Thank you.
So this week we are going to talk about stepper motors and DC motors and all kinds of motor control. So, but before we do, I want to show you a little bit what I've got this past week to play with. So this is some of what I got in this last week. I have a couple more small ones that aren't so many, but basically it's a bunch of shields. You see, this is a shield that goes to an Arduino Mega. It's a breakout shield for monitoring tally lights and stuff, but it can be used for anything. It's a general GPIO for field or shield. And this shield is actually, you see how much bigger it is than the Mega. The Mega fits inside this shield, and then on top of it, through this hole, is an Ethernet shield. And maybe I'll try to show it by the end of the show. But it's a jumper board, basically, to go to all the boards for the switcher. And then I have some development test boards for different types of I2C chips right here. This is a dev board, which basically holds a breadboard and pins to go from the Arduino, and you can go into a breadboard that's attached right to it. Another breakout board. So lots of things to play with this week. So that was my fun-filled week, is putting those together and testing all that stuff.
And it does look like fun.
Yeah. It's a lot of surface mount stuff. I'm getting much better at that now. the more you do it, actually, you can see here are actually 3 of the shields for testing the I2C stuff. You can see I've already surface mounted the chips, but I haven't put the rest of the components on it yet.
Nice.
Yeah, it's getting a little easier. I got that reflow board, and it actually works pretty good, although I think it would work better if it was in an oven. So I'm going to try to modify an oven this weekend. I have an old oven in my wife's that I can use. And
okay.
Basically, you just drill a hole in through it and put the sensor inside, and then you use a external relay that controls it. And there's a profile already in there that looks like it would match pretty much what I needed. So I'm going to give it a shot and see what it does. The only problem I'm having with surface mount stuff is I'm putting too much solder on the chips, and it's so sensitive. It's so tiny. It's so hard to get that little bit of solder on there. So, okay. So let me clean out the stuff here. So this week we want to talk about a couple of things before we go too far. We want to talk about H bridges, which is what controls the motors, and then we want to talk about stepper motors. So I found a couple things on the internet I'm going to walk through that gives a pretty good example of what an H bridge and what a stepper motor is. And actually, the stepper motor one is actually from Wikipedia, so it's a very easy one to find. But let me go and show you this page here on H bridges theory and practice. So I've actually found this, and actually the page is a little bit old. However, the information in the page is actually still very, very relevant, and it talks about the H bridges theory and practice. And I'll put a link to this in the show notes. As you can see, it's last updated was December 23rd, 2006. However, the technology behind an H bridge is still an H bridge, and it's still used pretty much anywhere you have motor control. So it's going down here a little bit, and there's a little bit of basic theory, and here's why you can see it's called an H bridge. See the motor right here in the center, and if you take away this little connection right here, it looks like an H, and that's why it's called an H bridge. So the basic theory behind it is it allows the motor to turn 2 different directions by turning the voltage backwards. So in going one direction, you have positive on one side, negative on the other side, and going the other direction, you reverse that, and you have negative on the other side where the positive was, and positive on the side where the negative was, which turns the motor the other direction. And the H bridge allows you to do that. And you can see here's the high and the low side. We're going to call them left and right, just because it's an H. So basically, if you want to go one direction, and in the case here where the motor has plus and minus, we're going to say this goes clockwise. So you would close this button right here, the high side left, and this button right here, the low side right, and it would turn clockwise because you are putting positive in this side, and negative goes out to this side. And if you reverse that, say you would take and turn, these two are off now, and you turn the high side right on and the low side left on, it's going to go counterclockwise. Again, it's how your motor is wired as to which direction it goes, but it basically goes the opposite direction. Now there's some things you can do in here as well. If you would take like both the left and the right low sides and close them, the motor would tend to break because it doesn't want to generate electricity. So there's some tricks, other things you can do with this as far as braking goes as well. And if we scroll down this page a little bit farther, here's exactly what I just described to you, where high side left and low side right are closed, and the electricity travels in this direction, just like that. And it's exactly the opposite. So here is what I was just talking about: high side left, high side right off, lower left off, lower right on. Motor goes clockwise, and reverse that, motor goes counterclockwise. And if we have either the two highs or the two lows open together, the motor brakes. So there's also another good reference to an H bridge, and it's actually at Wikipedia. Of course, everything's in Wikipedia, but there's a great example in Wikipedia also describes an H bridge and kind of tells you, pretty much what we just did. Now here they're showing you a very powerful H bridge, which is the kind of H bridge that I actually use in my CNC machine for the stepper motors, because they're much bigger than what we're running with in the projects tonight. So this handles a lot more. You actually see it has a big heat sink on it, and if you, as I mentioned before, if you look at the chip design, and we're going to get to that here in a second, you're going to see that because of the heat dissipation, it actually designed the chip a little bit differently as far as pin layout goes, and we're going to talk about that here next. But I'll put this link to Wikipedia here as well. It's another great reference to H bridges, and plus you also go to different stepper motor links and stuff like that too, for if you want to go and read a little bit more about that. All right, so let's go look at the actual chip we're going to use tonight, and we're actually using a TI chip, and it is an L293D. And it's this package right up here at the top, and this is the D package right here, or the D. And if you look at it, you basically have main thing what you see here is in the very beginning you see heat sink and ground. So 4, 5, and 12 and 13 are ground pins. So if you look at the board design, especially, I know ours for sure when I designed mine, is I made sure that the ground fill was there so that it helps dissipate the heat from these chips, because they do tend to get a little bit warm. Our product tonight won't get that warm because the motors we're using are actually rather small, but it's something to consider. And the actual shield that I'm showing you is actually using a socket, which I do not recommend using a socket for a permanent application where you're going to run motors all the time, because it's not a very good heat sink. So that's just something to kind of keep in mind there. So you have here your two, see 1AY, 2AY, 3AY, and 4AY. So this is basically similar to 4 H bridges. And is that right? No, that's not quite right. I'm sorry. It's 2 H bridges. I got it wrong in my head. So you basically have a 1 and a 2 and a 3 and a 4. So if you're running a DC motor, you can run 2 DC motors off of this. And we're going to show you just 1 DC motor tonight. But in the case of a stepper motor, when we get to explain that here in a little bit, they basically have the equivalent of the windings of 2 motors in them. And by using the 2 different windings in a roundabout pattern, it likes the motor step by step by step. So in our case, this is the equivalent of 2 H bridges, where like 1A and 2A are part of the H bridge. and so as Y, as long as also the 1Y and 2Y. If we go down here a little bit, you're going to see a little bit better diagram of this. So here you see the actual H bridge, and you see it's a sideways H in our case right here. And you come over and you see pin 6, which is the A pins, and pin 3, it basically controls, one goes to each side of this coil. So this is considered to be a DC motor, and based on what you put in as far as pin 1 determines the direction that it's going to go. So, and the same way goes with this other half. This is the other H bridge on this side. Now you see they're not showing an actual H bridge on this side, they're showing two separate DC motors. This is also, it can control a motor in one direction you can adjust the speed by using pulse width modulation of the motor, but when you run it in this mode, it does not control the direction of the motor. So if you were to run this as another H bridge, you see you have an H bridge on this side and an H bridge on this side. And let's go down here a little bit farther. So anything else interesting in this document? And I call it half H. I never heard that before. Let's see if we can look at some of the characteristics of this. Another block diagram of how this is all working. Let's see what else can we get in here. And I'll put a link to this. This is just one H driver. There's a ton of H drivers out there, and this is actually a fairly low power. So what I was trying to find was the actual power rating itself. Well, I think it's probably at the top up here. Let me go up here and look. So yeah, it's 1 amp per channel, or 600 milliamps. For our one we're doing is 600 milliamps for the 293D. So at a peak, it's a peak output current of 2 amps per channel, and let's see, there's a voltage rating anywhere? I think, oh, there it is, 4.5 to 36 volts. So it's a pretty wide voltage range as well. So this is a very a good utility chip to use for doing an H bridge. Now you can get single H bridge chips as well. In the case of this shield I'm using tonight and the one that I designed, I actually used this exact same H bridge because it's a very nice H bridge, not that expensive, and it's well known. You can see, actually, you could look at the date of this one is September 1986. So it's had lots and lots of usage to it, and it's been revised. It was revised in November 2004. Even 2004 is a long time. So it's a very reliable, well-known H bridge. That's why I went ahead and used it in my project as well. All right. So the other thing I want to walk through is stepper motors. And this is a little confusing subject for a lot of people. But again, we're going to go to Wikipedia, the place for all knowledge, it seems like. And you can see here on the right, there's actually a moving image as an example. And one of the things you will notice here is this is a 4-coil stepper motor, 1, 2, 3, and 4. What we are actually using is a 2-core, but with micro-stepping, it acts like this 4-core. So basically, what happens is you turn on the 1 core and it steps, and you turn on the next core with the current core on it, and it steps halfway between, and you turn off the first core and it steps the whole way over. So using micro stepping, you can do the same type of thing you can as with you had 4 coils. In fact, it's very rare, I think, that you actually find 4 coils. I don't know of actually a motor that I've ever seen that had 4 coils in it for a stepper motor. But you get the idea, is each step takes it one little piece to go the next step. Now the gear I'm going to use tonight, it's 69 steps per rotation, and supposedly from what I can find on the internet, the gear is geared down so to 69 steps per rotation. So it'd be 69 times 69 steps to make the shaft on the motor turn one complete 360-degree revolution. And I can't say that I've actually checked it to confirm that, but it's probably pretty close to that based on what I have seen. So here, if you go down through here, they're going to show you a couple different kinds of stepper motors. There's the unipolar stepper motor, which basically is one winding with one center tap per phase. And then you have the bipolar, which has a single winding per phase, and the current in the winding needs to be reversed in order to reverse the magnetic pole. So when we get out to the stepper motors like I'm going to talk about, we're actually going to use micro stepping. So I think going down here, it does talk about micro stepping. Okay, here's full step, half step. So basically, what a full step is the usual method for a full step driving motor. 2 phases that are always on, and it'll have a full rated torque. And then when half stepping, the drive alternates between the 2 phases, which is kind of what I was explaining before. You go 1 phase on, next phase on, 1 phase on, next phase on. The thing is, it's not quite, it's a little jumpy, and it's not as precise as micro stepping. So with micro stepping, they say anything about a waveform. I can't say that I've ever actually looked into the details of the waveform change, but it basically, what it does is it takes and does, there's a combination of things. It's kind of like half stepping where 1 phase turns on, another phase turns off. In this case, phase 1 turns on, then phase 2 turns on, then phase 1 turns off, and then it basically goes around in a circle like that. So you keep changing which phase turns on, and they're like halfway between. So you go from 1 on to both on to 1 on to both on, and that's micro stepping. So it turns it in much greater detail. It's much less vibration in that motor as well. And we're going down through here, it's going to talk about some of the theory of the different things and different amount of torque. Each type is different. And here's the ringing and resonance I was talking about. I call it shaking, but it basically is, they call it resonance in here. And that's because the motor is fighting basically magnet to magnet. And then it talks about different applications and some of the ratings you have, stepper motor systems. And the thing to remember is, since you're using 2 coil windings, you're going to use 2 H bridges per motor. So in the case of our example tonight, I'm actually using 5 wires to control the stepper motor because I have 1 common, and then there's basically, I want to say 4 coils, but it's not necessarily coils per se, but they're all different windings. I'm going to go ahead and we're going to walk through this program before I actually show you this. This is a sketch that is created using last week's encoder. So if you haven't seen last week's episode, I would go out and watch it if you want to know how encoders work. And that's episode 35, where we cover how to use encoders. So I've taken the code from last week and I've integrated it in with a motor control. And I'm going to scroll down here a little bit. And we're going to see right here. First of all, a couple things you're going to notice right away is we have Excel stepper and AF motor. And AF motor is Adafruit, because I'm using an Adafruit shield for this, for the demonstration. And Excel stepper is like a wrapper. That's how the best way I want to say it. So AF motor is like the driver. It knows how to do the steps with the chips that are on there. Excel stepper, you give it the routines. So like basically when you define Excel stepper, and you're going to see it down here, you tell it to step forward or backward. Here's the routine that you call. And that allows it to be generic across almost any kind of stepper control, because you call the routine is going to make the motor move forward 1 step. And Excel stepper has some cool things built into it. It has the ability to speed up as it starts and slow down as it stops. So it doesn't like start out at full speed. It builds up to speed, and when it gets close to stopping where it needs to go, it'll start slowing itself down. So it has acceleration and deceleration built into it. So a couple other neat things like that. That's what these 2 libraries do up the top that are included. And here at the top, if you remember last week's episode, we actually defined 2 encoder pins. You will notice I am using 53 and 51, and that is because so I had access to some digital pins to add an encoder. I used an Arduino Mega, and these pins are down at the end where I can easily access them because the shield that I'm using for the motor control is taking up all the pins. So that's why I'm using a Mega. There's no other reason to use a Mega other than I needed some more pins I could actually get to. And then we have our encoder position and our encoder A and B last, and so you remember all of this from last week if you watched that episode. So here is the next new thing, and we actually define our motor, and it's AF stepper, and we are saying that it is 200 steps per revolution, which I do not believe is correct, but I'm just going to leave it like this for now. So, and then we are motor number 2, because I'm using the right side of this shield this week for the stepper motor. And then we come down here, and remember I said about you define, or it's like a wrapper. So here is the routines: forward step and backward step. And basically it's calling motor 2, which is the Adafruit library, which is the low-level library, saying do 1 step forward, single, and here's 1 step backward, single. Here's where we come down and we define the Excel stepper class, and we are going to call it stepper 2. And basically what we're saying is to go forward, call this subroutine forward step 2, which we just defined right here, 1 step forward. And to go backward 1 step, you call this one backward step right here. So now this wrapper can control the motor because we told it where the functions were to do that. All right, so we're coming down through setup, and a couple of things we're going to set up here. The stepper, we're going to say its max speed is 500, I think it's per second. And the acceleration is at 100. And when we start out, you can move to 0. And that's just so we know where it's starting at. That's the main thing we do that for. You can move it to anywhere you want. We just want to make sure that we are starting it at 0. And then we do our encoder stuff right here. Pin mode for the encoder pins A and B are both input pull-ups. And then we come down to our loop, and we do what we did last week. We read the encoder pin A, and if encoder pin A has changed, then we look and see is the encoder pin A high, and if it is high, is encoder pin B low, or no, if it's low, is the encoder pin B high, and based on that, we know if we're going forward or backwards. So here we're going to say motor 2 step, and this is the number of steps. Now here's why it says 100. If I did 1, you would never see it move. When I first did this, I had in there 1 or something like that, and I thought it wasn't working, but it was working. So what I'm going to do is every time the encoder turns, I'm going to turn the stepper motor 100 steps backwards in microstep mode. So basically that means I'm turning the encoder counterclockwise. And if I'm turning the encoder clockwise, then I want to step 100 steps forward, just like that. And then we come down, and here's the encoder pin B. And again, it's the direction. So if in this case, we're going to go forward 100 steps because I'm apparently turning the encoder to the right or clockwise. And otherwise, I'm going to go backward 100 steps. And then I do the encoder pin last A and B at the bottom, which is, again, from last week's show. So I am going to upload this real quick, and we're going to hop over and watch it run. And it's loading. There it goes. All right, so if you see the motor is sitting still, let me move the encoder over here so you can see what I'm doing with it. I'm going to hold it, turn it, it's a little sensitive, but I'm going to turn it clockwise. Try to. There it goes. So you can see that the stepper motor is turning the same direction that I'm turning the encoder. And if I go backwards, it goes backwards with me. Just like that. So that's what the encoder is doing, is turning the little tire a little bit at a time. So we talked about the encoder last week. I'm going to show you the code for this because the library is actually very simple. Now, if you look at the actual board itself, there's basically 3 chips. So we have right here is the H bridge, and this is another H bridge. And in the center is a 595 chip, which we talked about in the past. So this is actually
my favorite chip.
Yeah, it's your favorite chip. That's right. So
it's used everywhere.
Yeah, so we're using a 595 to send the pulses to these H drivers right here. So each H driver has 4 inputs. The 595 has 8 outputs, so it matched up just perfectly. And you can also see there's a 10K resistor, and that's just to hold the pins low for the H driver. So when it first turns on, it doesn't start spinning a motor when it shouldn't be. I want to show you something else here too, and it's actually built into the library here. into the, when you download all the Adafruit stuff, it comes kind of with it. And I'm going to go into an example, and we're going to go, examples. And we're going to go look at the Adafruit library, and we're going to do constant speed. And we're going to choose that, and let's go ahead and make a full screen here. So first of all, as I mentioned before, our motor is actually motor 2 on this board because we have the DC motor on motor 1. And we're going to scroll down, and you see 200. 200 is the default, I guess, for this library. But what I want to do is just see that the set speed is 50. So what this is going to do, it's going to make this stepper turn at 50 pulses per second, and you're going to need to see how fast it works. So I'm going to go ahead and upload this real quick, and go ahead and watch it. Okay, you see how slow it's turning? That's 50 steps per second. Turning very, very slowly. I'm going to go ahead and I'm going to increase that speed to 200.
Great precision there, isn't it?
Yeah, that gearing down is pretty precise. All right, that's 200 steps per second. Still very, very slow.
Yeah, this would be great for where you need to move something in very small, precise increments.
Right. Most the stepper motors like I use for like on the CNC doesn't have that gearing down like this one does. So it's a little different. I'm gonna go with 500. I don't think that's the maximum for this is 500. Yeah, so that's 500 right there. Still very, very precise, very slow. And it's because of the gearing down, it has a lot of torque behind it too. You can't like just stop it real easily. It'll turn out your fingers pretty nicely. All right, so that is the stepper motor. So the other motor next to it, the DC motor, again, you can see only 2 wires. See, there's 2 wires running to this right here, where there's 5 wires running to this. So basically what's running to this is, in the center is a ground, and then each of these wires is half a coil. So 2 wires go to one coil, and 2 wires go to the other coil in the stepper motor. And because of that, they can half step across the common in the center, so you can kind of go like half the coil on and half the other coil on. That's like it's considered a micro step, and it allows you to be very precise. Okay, so let's go back over to the code, and let's switch over to the other one I have here, which is encoder motor. And we'll walk through this one here before we show you. Basically, what I'm going to do is I'm going to set it up so that the encoder controls the speed and direction of the DC motor. So if I turn the encoder clockwise, the motor will turn clockwise. And the more I turn the encoder clockwise, the faster it will go. And then if I turn it counterclockwise, it'll slow down until it stops. And then if I keep going, it'll start going counterclockwise. And the more I go counterclockwise on the encoder, the faster counterclockwise it'll go. So let's walk through this code a little bit here. And it's going to be very, very similar starting out here. It's the Excel stepper and the AF motor. And we're going to come on down here, and we're going to define our encoder pins, 53 and 51. I have now changed the encoder value to be motor speed, though. That's the only thing that's changed right here, but everything else is working exactly the same as it did before. Just it made more sense to call it motor speed, so I just changed its name. Come on down, encoder pin A and B. The N is the current value. And then here you see I do AF DC motor, and it is motor 1. So one of the things I should probably come back and say, just so it's not confusing, is I left the Excel stepper in here, but it's not used by this application. It's just because I copied it from the other one, because I wanted to basically do the same thing, just changing the speed of a motor instead. So that's my mistake there. I should have gotten rid of this so I didn't confuse you, but that is not needed, just so you know. Okay, so we defined our motor in motor 1. On this particular board, we're using the if you're running DC motors, there's 4 motors. Motor 1 is the top left, I guess if you look at it from that point of view, and motor 2 is the bottom left, and then top right is motor 3, and bottom right is motor 4. I'm using motor 3 and 4 for the stepper, so that's actually 3 and 4 equal stepper 2. All right, so we come on down, and we're going to set our speed to 0, so it's stopped. And we're going to basically do run release, which is the equivalent of doing stop. I set speed to 0 just so I knew where it was coming in here. And you actually see some debug code where I was actually experimenting with the forward. And then I define the encoder pins, so they're both input pull-ups. And then we come down into this very familiar now encoder loop. And what you're going to see here is I am going counterclockwise. I am decreasing the motor speed value by 10 for every left click of the encoder, and for every right click or clockwise click of the encoder, I am increasing the motor speed by 10. And I'm doing it down here as well, so I won't go through the details of the encoder again. But and then we come down here, and you see I still have debugging code. Easily removed. You see I'm setting my last pins. Okay, so here I'm basically saying if motor speed is greater than 10, then I want you to do this. I want you to come in this routine. And if motor speed is greater than 200, basically all I'm saying is the maximum you can go is 200. I don't not know what the maximum value is, particularly with this motor, but I know 200 works fine, so I set it as the maximum. And then I do a motor set speed, and I set motor speed, and then I tell the motor to run forward. So the reason we do this greater than 10 is it gives us a little bit of play in the middle. So 10 barely moves the motor, and actually it sounds like it's not, actually I'm not sure it even does move, it just sounds like it's vibrating. But the other thing is this gives us from positive 10 to negative 10 as a stop area. It doesn't have to be exactly 0, so that makes it a little bit easier to find the stop area as well. So if it's greater than 10, which means we're going to go forward, I'm basically saying set the speed and then run forward. If it's less than 10, which means I've turned the encoder to the left past the 0 mark, then I'm going to check again, see if the value is negative 200, and you'll see why in a second here. And if it's less than negative 200, I make it equal to negative 200. And then I do motor set speed, and you see I'm doing the absolute value, which turns that negative 200 into 200, for example. And then I say run backwards. And that's because negative numbers don't make sense in a speed value, but negative numbers make sense in the encoder. So I'm basically taking the negative value of the encoder, making it positive, and say run it backwards. And if it's in between, so if it's less than or equal to 10, or greater than or equal to negative 10, then I'm doing this release, which basically makes the motor stop. And that's it. It is that simple. So let's hop over and watch it run. And it's done uploading. And what we're looking at now is the black one here on the right. And the black piece should start turning as I turn the knob to the right. So I'll go to the right. And there it goes. And the more I turn, the faster it gets. Until it gets this, that's probably about the fastest it's going to go right there. And if I go counterclockwise, it'll start to slow down. And there it stopped. Okay, I'm going to keep going. And now it's trickling backwards. Actually, if you kind of listen, you can kind of hear it. It's so low at that point where you can kind of hear it trying to go, but just won't go. And then it keeps going faster and faster and faster until eventually it gets to the negative 200 value, which is the maximum. And if I go clockwise, you'll see it starts to slow down till eventually it gets to the point where it stops. Then I can go back the other direction. So that's controlling the speed of the DC motor. Now, these libraries are very easy to use. I was actually surprised at how easy it is to use those libraries. These are Adafruit libraries, and it gave me some ideas when I was creating mine of things I could do. So they added a lot of cool features. They can just change the run direction, you have to set the speed, or you can go down to the detail level. And the way they implemented the other library, which manages the the higher level features of the stepper motor by calling a lower end library was kind of cool too. How I did that, because when I was writing mine, I was putting it all into one library, not looking at the other library to do all the extra work for me. So I think going forward, I'm going to go back and rethink how I did my library, because that library is free and open, and if somebody uses that, they can change out the stepper motor undercarriage of it, and it'll still work just fine. It's a neat idea.
Well, it's nice when you have a good library to work with, isn't it? Yeah,
and it makes it very portable. So if somebody wanted to use my hardware or my library to do my stepper, but then wanted to go to Adafruit, they could just switch out the underlying code of it, and it would just work. They wouldn't have to change all the upper code out. It was kind of neat how they did that. So, all right, so that is stepper motors. Stepper motors, DC motors, H bridges, everything like that.
And you used relatively slow speed motors, but the same principle applies, particularly with DC motors, that you can use essentially the same thing for, if you had a little robot.
Exactly. Actually,
that you were running
these are actually 4 robots. The tire came from a robot, the same motor, but the same DC motor, but in a different gearing scenario.
Right.
But I just wired that one up and didn't realize I'd gotten the wrong one. But yeah, that's what those motors are from.
Yeah, with that gearing, you're looking for precision, not speed.
Right. Well, yeah, no, I'm talking about the DC motor. Yeah.
Your DC. Okay.
Yeah. The only reason I put the tire on this one is because it fits the shaft better, and I could tell when it was turning. Because if it was like that, you could never see the thing turn, so we wouldn't be able to give you a good example. So it's fine when I was sitting here looking at it myself, but whenever I put it on camera, it makes it a little hard to see what it's actually doing. So I'll put links to all the libraries in the code and everything up in the show notes, and also to the H-bridge document. Although it's an old document, it gives a great example of how it works. So I'll make sure all that stuff's up in the show notes, so for everybody to get and look at. Anything from your side?
No, I think you've covered it fairly well. I mean, and some of this stuff, H-bridges, they've been around for a long time.
But yeah, a long time, yeah.
Stepper motors have been around a long time. The principles aren't terribly new. So even though the articles aren't, they're several years old, there's really nothing to have changed. So the principles are the same.
Yeah, no, I didn't look before I came on to see what actually, I may still have it open here. Let me see if I do. To see what the maximum on the H-bridge was. Yeah, so I have it open here. Let me see what it was. Because these still, after me using them, are not getting very hot. These aren't even warm, so it could probably pull a lot more through it than what I was doing. Well, it says it'll do 4.5 to 36 volts at 600 milliamps. I'm not pulling anywhere near that. So it could probably do some.
You're using the L293, right?
Yeah, 293D. Yeah.
Yep.
And I haven't had it. I've been checking the temperature to see if I was getting things too hot with what I was doing, because I didn't really measure the motors before I stuck them on there and started playing with them. I figured that the stepper motor wouldn't draw that much because it's a really small stepper motor. It's not like my big CNC ones that weigh 10 pounds a piece. It's very light, and because those definitely would draw much more than what this thing can handle. Yeah, 600 milliamp is what it says for 293D. So it's
1.2 amp total.
Right.
Off the 4 channels.
Right.
Which that's still a lot of current going through a tiny little chip.
Oh, yeah. That's a lot. That's probably why it gets so warm. I noticed in the design of the Adafruit board, there's definitely a lot of copper in that area, which is probably just to keep the heatsink, working. They also make a larger one, right? The DWP, is that what it is? Oh, but it's...
H-bridges themselves can come in a whole range of, if you can dream it up, there's probably a... Yeah,
the ones that I have for my CNC machine are really big. The pins kind of bend down from the top, and there's a big heatsink on top of them, because they're driving those big motors. All right, well... That's it, I think, for this week. A couple reminders. If you are on YouTube, you can go to youtube.com/TechZenTV and get all our videos. All of our shows are on that channel now, but we have them separated out in playlists, so that if you want to watch one particular show, you don't have to watch all the shows. I've had that question before. We definitely put them into a playlist. So if you're just interested in this show, you can just watch this show and not have to watch all of the other ones that are out there. If you're following us on Twitter, it's at TechZenTV, and if you do tweet about this show, use the hashtag #Let's Make It. And also Facebook.com/TechZenTV is our Facebook page. I think just about everybody's on Facebook. I'm on Facebook, although I don't use it a lot. But we do have a page out there for TechZenTV, and you get to see all the shows and stuff like that we actually release. And if you want show notes, you can go to techzen.tv and then the Let's Make It show, or a shortcut is actually to go to letsmakeit.tv. It takes you right to the page where all the stuff is actually located. And we do record this show at 9 p.m. Eastern every Monday night. And next week, what we do next week? Do we have any plans for next week?
I'm hoping I have my Rainbow Arduino going. Yeah. I finally got it to wiggle over the weekend.
Got the wiggle. He has the wiggles?
Got it to wiggle. Well, last week when I first got it, all it did was blink one red LED. So I've gotten around that problem, and I actually have it doing it's making blinking lights now. So hopefully by next week I'll have something interesting and useful to show.
That sounds like progress to me.
Yeah.
anything that wiggles, right? It's moving.
Yeah, that's right. It's wiggling.
Yeah. So
very technical term right there.
Yeah.
So.
Has the wiggles.
Wiggle.
Yeah, I don't remember what I had on my list for next week. I'll have to look. I thought I had it all planned out for the next couple weeks. I don't remember what it was. Oh, well.
Well, and I've got a couple other projects that I'm working on. One of them we've talked about that I'm not ready to publicly disclose, but I am working on it. And then I've got a viewer that I've been working with off and on for the last month or 6 weeks, and I'm finally making some progress on his project. So I had to step away from it for a couple weeks. So yeah, I'll have a little more coming up in the next few weeks.
Okay, good. I don't remember what I had. I had something already planned for next week, but I'll figure out what it was.
Okay.
We'll be a bunch of things in the queue. I just don't remember what I was going to work on for next week. All right. We'll see everybody next week, next Monday, 9 p.m. Bring your friends.
Good night, everyone.
Come chat. All right, night.
Good night.
For show notes for this show, contacts, and more, go to the techzen.tv website where you can get show notes for all of our shows. We love to hear from our viewers and listeners. We have an email, a Twitter, and a phone number where you can contact us for each show. For details, visit the techzen.tv website and get the show details. You can also make a video and upload it somewhere like YouTube or Vimeo, and then just send us a link. You never know, you may see your video in a future show. You can get all of our shows delivered automatically to your favorite device by going to your favorite podcast website like iTunes and subscribing. Each of our shows also has a YouTube channel you can subscribe to get regular updates. Our shows are also available on most internet radio networks like Stitcher and TuneIn Radio. You can also watch and listen to our shows on Xbox, TiVo, and Roku. You can even find us on your Zune.